So far, we've been thinking about knots up to this idea of isotopy, that is, deforming the knot in some way, right? And we say two knots are equivalent if you can deform the knot in some way, and so this knot is equivalent to the unknot, right? And so far, we've been thinking about knots in R3 equivalent up to this thing called ambient isotopy. And the way we studied these is we said, well, in order to see if two knots are equivalent, well, sometimes it's tough. You might have a knot like the trefoil, and it may not be obvious. Like, is there some way to deform this to get back to the unknot? And it's like, that's hard. I don't know. It doesn't seem like it. And so we came up with invariance. And so what is some of the invariance we've talked about? What was the first one we talked about? Yeah, we talked about colorability. Colorability. So the trefoil is colorable, but the unknot is not. And so that's how we know the trefoil is not equivalent to the unknot, because no matter how you deform the trefoil, this invariant will stay the same. Since it started off colorable, it will remain colorable. And so there's no way to end up with the unknot, because the unknot is not colorable. What was another one? Yeah. And there was a nice connection between the colorability and the determinant. And that's it's p colorable if and only if p divides the determinant. And then we had some polynomials. We saw the Alexander, which relates to the Conway, so the Alexander-Conway polynomials. And last time we talked about the Jones polynomial. Oh, we also did, the cipher surface, which gave us this genus. So we talked about the genus. And so this was a toolbox of invariance we've had so far. And it was all addressing this fundamental question of when a knot's equivalent. We then talked about a couple alternative ideas of equivalence. So one of those ideas of equivalence was this idea of some kind of local moves. Like maybe we allow it to move through itself, right? So that gives the idea of homotopy, so link homotopy. And we had these delta moves, and we start seeing some other ones. What I want to do today is build up to another notion of equivalence. And so to do it, let's generalize the idea of an unknot. And so we're going to try and generalizing the idea of an unknot. And to do this, instead of thinking about knots as living in R3, so typically we think about knots and links as living in three-dimensional space in R3. Well, instead what I want us to do is to think of them as living in S3. So here's what I mean by S3. When I say S2, that's just my notation for the sphere. So this is a two-dimensional surface. This is a two-dimensional sphere. And the sphere is related to R2. In that the sphere pretty much is the plane, except as you go off to infinity, you actually have some point at infinity. It's like this top point, right? And so you've seen this like stereographic projection before. Like you can project the sphere onto the plane where there's a nice 1-to-1 correspondence between points on the plane and points on the sphere. And as you go off towards infinity, you get closer and closer to this point on top. And so you should think of the sphere as pretty much just you have your plane, but your plane is wrapped up into the sphere. And so points, as you go to infinity, you're approaching this point at the top. Good? OK, so that's what I mean by S2. Similarly, you could talk about S1. So what do you think I mean by S1? Yeah, so instead of being a two-dimensional sphere, it should be a one-dimensional sphere. And that's just going to be the circle. And that's a cousin. It's closely connected to the idea of just the real line. And what's the relationship with them? Well, you just wrap the real line up into S1, where now you have this point at infinity. So as you go off to infinity, it's like going around, getting up closer and closer to this extra point you've added at infinity. Plus and minus infinity are both this point, this north pole. And there's a natural association of a similar projection you can do of associating points in a one-to-one way. Each point on the circle corresponds to some point on the line, and you're left with this point on top corresponding to the extremes at infinity. Comfortable with that? So sometimes you call this the one-point compactification. So by adding a point, we move from this space that was unbounded to a nice bounded compact space. So in some of the other classes, you may have heard language like this. So what S3 does is a very similar idea. S3 is going to be the three-dimensional sphere, which you should think of as R3. So this is just like three-dimensional space. But as you go off to infinity, there's actually a point there. And so there's some point. And so S3 is a nice compact version of R3 that has this point at infinity. And so if you keep going, eventually you hit that point. Like here, you keep going, eventually you hit infinity, and then you come back the other way. So it's the same thing like an R3 compactified into S3. So for simplification, I often think of my knots as just living on a sphere, right? But instead of being the two-dimensional sphere, it's one dimension higher. So this is just my one dimension lower representation of S3. Okay. But here's the key point. S1 bounds a disk, or you might just say it's a disk, but I'll call it the we'll just say it bounds a disk for now. So S1 bounds a disk. S2 bounds a ball. So S2 bounds inside of it some ball. And so S3 similarly is going to bound some kind of creature. If I call this ball, well, this is a three-dimensional ball, and so I can call it, it bounds the ball B3. I'll say that this bounds a two-dimensional disk, so it bounds the disk B2. S3 will bound some four-dimensional ball. So this is a four-dimensional ball. And so it's really tough to visualize because S3 is itself three-dimensional space, but it's like the sphere, it's bounding inside of it four-dimensional space. In the same way that S2 is a two-dimensional surface that bounds inside of it a three-dimensional space. And S1 is a one-dimensional manifold, it's a one manifold, and it bounds inside of it some two-dimensional space. Is that clear? So you think of S3 as like living around this four-dimensional ball. And it's really hard to like visualize it. So I'm just going to draw it in the same way as I drew it here, one dimension lower. But you should think the surface of this is actually three dimensions. And the stuff inside of here is four-dimensional stuff. It's a four-dimensional ball, B4. Okay. So if that's the case, if I now think of my knots as living in S3, that means that when I say I have some knot K inside of S3, the right way to think about it is your knot is living in three-dimensional space, but that three-dimensional space is on the surface of some four-dimensional ball. So it's like, here's my, it's a lame knot. Here's my trefoil. What's going on? And this trefoil is living in S3, but that S3 is just the surface of this ball. And then inside is four-dimensional space. Okay. Recall, we say a knot is the unknot if and only if K bounds a disk in three-dimensional space. So for us, there's R3, we could say it's S3. So only the unknot bounds a disk. But what we want to do now is we want to generalize this idea a little bit. And instead of asking, do you bound a disk inside of three-dimensional space, we're going to say K inside of S3 is slice. So this is my definition. If and only if K bounds a disk in the ball. So we'll say that subknot is slice if going into the ball, it bounds some disk. So this is a little bit trippy, but you follow? Any questions up to this point? Well, I'll show you an example in a second of a slice disk that of a slice knot that will hopefully make this clear. But let me just say one more word. This definition is a little bit too weak because any knot, so warning, given any knot, you can say it bounds some disk in this four-dimensional ball by just taking a cone. So you pick some point, and you just like project this down onto that point, and it makes a cone. So like at each cross section, this cone is a copy of that knot, but it's a smaller and smaller copy. So this would have every knot bounds a cone. And that cone is a disk. So every knot bounds some disk in the four ball. So as you go down into the ball, as you go down off the surface a little bit deeper into the ball, at each level you get a smaller and smaller copy of the trefoil until it vanishes at the point. But you might imagine like, yeah, but when it vanishes at that point, it's like just poof. You know, like it was a trefoil and it poofed out of existence. It turns out this is a singularity. It's not well behaved at that point. And so we want to avoid this case. And so I'm going to say it bounds a smooth disk. And by adding the word smooth, I just mean it bounds some nice disk that doesn't have some singularity point like this. This is exactly analogous to calculus, where you wanted to avoid things like that weren't differentiable at that point. And so you said, your graphs had to be nice and smooth, so it would be nice and infinitely differentiable, things like this, right? So that's what we're saying here. So something to slice if it bounds a nice smooth disk. So you're probably thinking, like, what in the world are we talking about? So let me show you some examples, and hopefully it'll make it a little bit more concrete. So here's an example to make the definition of slice more concrete. So this is the knot 6-1. He looks something like this. 4 twists in total. So here's 1, 2, 3, and 4. 1, 2, 3, 4. So this is 6-1. And what I want to convince you of is 6-1. You think of it as some knot. This is representing 6-1 living inside of S3. What I have to show you is that somehow this guy bounds some kind of disk inside of the ball B4, right? So here's what we're going to do. The first thing I'm going to do is I'm going to just isotope 6-1 a little bit. So this is related by isotopy to grabbing this part and just moving it over. So that's going to give us yeah, still need my 3 twists down here. 1, 2, and 3. And I think this is right. 1, 2, 3, 1, 2, 3. Yeah. Okay. So I pulled it over. So I just isotoped it a little bit. So that here is equivalent to just coming down a little bit into your ball. And as I move down this part, I'm just isotoping the knot a little bit. So at this cross section right here, I'd have just this guy. But then, notice, if I give an orientation to this knot, comes over, comes up, and I zoom in and I look at this part of the knot right here. As I look at that part of the knot, I have one bit that's oriented like this, and the other bit that's coming oriented the opposite direction. And so what I'm going to imagine doing is I'm going to imagine these two arcs moving closer and closer together until they just kiss for a moment and then separate out. And notice I've done this in a way so that at the end, the orientation agrees, because this orientation should be going in and out, which is it's doing here, in and out, so it still agrees with the rest of the diagram. And here it should be going in and out, in and out. So I didn't mess up the overall orientation. And this moving from something like this to something like this, in our diagram is going to be equivalent to, well, what does this? If you think about a saddle, when you move down a saddle, this is like a Pringle, right? As you move down a saddle, you move from two arcs going this way, two arcs going the opposite way. So this move from moving from here to the associated diagram where we just reverse these arcs, I'll go ahead and draw the rest of the diagram in a second, should correspond with coming down and having some saddle that we move past. So let's draw this. So the rest of the diagram is going to look like, so this is just within the red circle. I just switch these arcs, and he should look like get that, and then he comes down, and we still have three twists. 1, 2, 3, 1, 2, 3, and then he comes up here, and he comes up here. Okay. That's not the clearest picture, but I think that's exactly keeping everything else in the diagram the same, just changing what happens inside the circle. Okay, but notice when we move through the saddle, prior to moving through the saddle, we had a single component, but the saddle splits it. So now we should have two components, a blue one and a yellow one. And if you look at this, sure enough, you have one component that's like this blue component. And you have another component, which is this yellow component. Tracking with that? Okay. Well, I still don't have a disk. I wanted this to bound a disk. So let's think about these components now. Well, if you think about this yellow one, you can grab this string on top, and you can pull it over. And if you pull it over, this is just isotoping it, and you pull it over, then you end up with some picture that looks like pulling the string over, you end up with a picture that looks like this. Right? So this was moving through a saddle, and now we're isotoping it. But this is equivalent to just, well, you take that yellow arc, you pull it through the trivial knot on two components. So you can isotope it again. And then, so you have exactly what we have here. And then what you can do is you can just cap those off. You can just cap this off. This bounds a disk, this bounds a disk. You just cap it off until they just vanish. And so you've capped them off. So I'll just say you then cap off. And so what you have here, it's a weird looking disk, but this is just a disk, topologically. It's just some disk that comes down and has some points, but it's just not. It's a nice solid surface, right? This is some deformed disk that just has two caps on it. So this is our slice disk, showing that this knot bounds a disk in B4. Comfortable with that? Does that make sense? Should we do one more example? Yeah. Let's do one more example of these to build our intuition a little bit more. So let's do, I think I had, oh yeah, here's another example. We can do the knot 8-8. So I'll again try and draw two stories at once. One is we have this disk, and each slice of the disk will give us like a little time shot. And we're trying to make this movie of it forming a disk. So let's try and do this. So here's the knot 8-8, and I want to show you that he slices well, that he bounds some disk, not inside of three-dimensional space, but inside of the four-dimensional ball. So he goes something like this. It then goes around, up, over, and comes down, and connects like this. Okay, this is 8-8. And I want to show you that he bounds a ball. So right now, he's sitting inside of some copy of three-dimensional space. And we're going to move down into the four-dimensional ball. And so let me give it some orientation. There we go. Okay. So we want to do a similar move where we pinch two components together, and we have this move where you end up passing through some cylinder from something that looks, like one of these to one of these, right? Because that's going to represent going through a saddle. Now, you might want to pinch together these two. But notice you can't, because the orientations are both going the same way. And since they're both going the same way, when you try to change it into from here to here, the orientation won't make sense, because like this one is going in, and this one's also going in. So it's like they collide. That doesn't make sense. So you can only pinch them together if the orientations are going opposite way. And so what I'm going to do is I'm going to take this part here and just loop it around. And by looping it around, he's still going this way, but now he ends up going the opposite way for a moment. And so now those two parts. Yeah. But sometimes you have to be kind of smart in where you pick it in order to make it easy. You can do it wherever and see what happens. But sometimes you don't end up with the picture you want. So if I do this right here, then passing through a saddle, so here's my saddle, passing through that saddle is equivalent to taking this and redrawing it like this. So now I've just passed through the saddle. So having passed through the saddle, I should now have 2 components instead of 1. And so let's check that I have 2 components instead of 1. So let me just start drawing. Yep, there's my yellow component and my blue component. And what can we do with these 2 components? Well, this back part of the blue passes, you can pass under the front part of the blue. And if you do that, it'll pass under, and you'll be left with just a blue arc like that. And then you can just, well, OK, let me go ahead and draw that. So this part, I'm going to erase this and say that's equivalent to this, where blue is passing over. And then what can you do? Oh, then I can just pull that blue down. So if I just pull that blue down, so now all this blue is gone because I pulled it down, I'm left with just a blue arc passing through a yellow one, which is just a yellow and a blue. And so then I can just cap these off. So the original knot, which is now erased, 8, is also slice. It bounds this slice disk. Good? OK, so there's a couple questions you might begin to wonder about. The first is every knot slice? So question. Is every knot slice? And in particular, sometimes I'll say smoothly slice. That's just specifying that my disk was smooth. But that's going to imply when I say slice, smoothly slice. Well, it seems like we have pretty good evidence so far that it is. But the fact that I didn't begin with the trefoil, and I instead began with these more complicated knots, probably suggests that, well, maybe this doesn't work for the trefoil. And in fact, it doesn't. Answer, no. The trefoil isn't. And by the end of the next lecture, we'll be able to see why it's true. But I won't be able to prove that today. But trefoil isn't slice. So the second question you might wonder is like, well, why do we care about this? You know, why is slice important? And the answer to that is what I want to talk about now. We're going to use this idea of slice to build an equivalence relation on knots. So remember before, we said 2 knots are equivalent if you can deform one into another. Now, knots are equivalent if they're related by this idea of sliceness. So here's my definition, really important definition. We say some knots, I'll call them K and J, are concordant. This is going to be my new equivalence relation. Concordant if K connects some, the mirror image of J is slice. Seems like a weird definition, but let's begin proving some properties about this, and I'll begin to try and show why it's more natural than you may think. So I claim that this is the equivalence relation on knots. In order to be an equivalence relation, what are the 3 conditions you have to satisfy? It has to be reflective. OK, so the first one is we need to show that this is reflective. So in particular, we want to say that any knot K is concordant to itself. So let's get some notation for concordant. So I'll say they are concordant, and we'll denote that K is equivalent to J, which means concordant to J. So K, let's just do one line. K is concordant to J. So we want to show that K is always concordant to itself. So that's what we want to prove. That's equivalent to saying we want to show something about K connect sum its mirror image. We want to show that this is slice. So why should that be true? Well, let me show you with the trefoil, and the example would be so compelling you'll believe it's true for any knot. Let me take the trefoil. So let's do this guy. And let me take his mirror image. So he's now going to look something mirroring it. So some line I mirror it over. So I get, mirrors are hard. I get this, right? Yeah. So here's the mirror in the trefoil. So this is K. And this is the mirror of K. And I'm going to connect some of these. And so I connect some of these. So now I have K connect some, the mirror of K. And I want to convince you that's slice. And so the way you should think about this is each point on K has a twin on its mirror. Each point has some twin. And so you can think about connecting that point with its twin via some line. And so you can connect each point with its twin. And you go around, and you'll keep doing this. You'll go back, it'll extend back here. You go back, you connect each point to, this is on the outside, so he should be going, here, 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 in the back. I connected each point with its twin. Now, if I had simply had, some circle with some circle, and they had been connect summed, then I would end up with just a picture that would look like this. They would be connected with its twin, connected to its twin. It would look something like this. And what is that shape? Well, this part's bending forward, that part's bending back. But if you were to straighten it up, that would just be a disk. It's like a disk that got the front, it's like bending around like this a little bit. So it would just be some disk. What this is, takes a little bit of imagination, but it's a disk that passes through itself a couple times. So the knotting causes the disk to pass through itself. So for instance, let's see if we can capture where it passes through itself. Like right here, as you're going in, you pass through itself at that part of the disk. And as you then come out, I think you're good, but I think you can pass through itself one more time down there. So this is going to be a disk that folds over and crosses through itself in a couple points. So it's tough to draw. The disk is being bent over and crossing over itself. Okay. But the disk crosses through itself. In three-dimensional space. And so what you're going to do is you're going to look wherever it crosses through itself. So let me try and draw a picture. Like here's the disk, and he's like crossing through himself, like right here, and then he keeps going. And so this is like disk crossing through disk. So what you do is whenever it crosses through itself, you just take a little neighborhood of where it crosses through itself, and you push that little region down into your fourth dimension. Because it's crossed through itself in S3. So this little white region of this part of the disk, you just push down into B4. And now it's no longer showing up to the other disk in S3. Right? So like here's your disk is up here in S3. and it crosses through itself like here. And so what you do is you just take a little segment of around that part and you just push it down. And so now it's like it's down here and it's in your fourth dimension. And so in S3, when the disk crosses through, it's no longer there, so it doesn't hit itself. So although the disk passes through itself in S3, you can push into B4 to prevent it from crossing through itself. Yay! And so with the trefoil, with its mirror image, it makes some disk cross through itself, be pushed down into B4, and now it bounds the disk. And for any knot, when you have any knot, and you have its mirror image, and you connect summit, similarly, it's going to bound some disk. And that disk, as it gets knotted around each side, is going to cross through itself in some regions. It's going to cross through itself. We're just going to push those regions into B4 to prevent it from hitting itself. And so any knot connect summit's mirror image would be a slice knot. It'll bound some disk, not in S3, but in B4. Happy? OK. Well, this discussion relates to an idea I want to introduce really quick, and we'll come back then to the idea of concordance. But I'm going to try and illuminate this idea a little bit more clearly by telling you about a special family of knots. So here's the special family. We call a knot ribbon if it bounds a disk that crosses through itself, so that is, it intersects only in arcs thusly. It only crosses through itself in this way. Here's my knot. It's bounding some disk. Over here, it's still bounding some disk. This knot is this disk is passing through itself, but it only hits in some arc like that. Yeah.
Do we still have two other things to show with the concordance?
Yeah, I'm going to come back and I'm going to show that it's both symmetric and transitive as well. But I'm hoping this, I think, was maybe a little bit unclear, and so I'm trying to make it more clear by unpacking what we just did a little bit. So in particular, just note, in particular, what we just discussed is we just said that K cross K connects some minus K is ribbon, right? Because it just bound some disk that crossed through itself in this way. And then what I was trying to do was to give you some argument to say it's actually not just ribbon, it's actually slice. But here's my claim. Well, let me give you another example of another ribbon knot. So here's a classic one. We can go around like this. He should, He should go around like this. OK, here's another one. Notice that this guy bounds some disk. It's like a long piece of ribbon. And that disk passes through itself a couple times, namely right there in an arc and right there in an arc. Right? Now, from the same argument from before, I'm trying to convince you that this is actually slice. So you see, what I'm trying to argue, I say lemma. Ribbon implies slice. Because whenever it passes through itself in some arc, you just push that down into your ball. And so it's still bound in a disk, but it's a disk in the ball that doesn't pass through itself. But if that argument's not compelling for whatever reason, notice how we can do something very similar to before. We think of this guy as just being some knot inside of S3. And then, let's give it some orientation. So he'll go around, and then he'll come back the opposite way. And he'll come back like this. And so notice right here, what we can do is we can pass him through a saddle. And when he passes through a saddle, he'll move from looking like that to looking like that, right? So passing through a saddle, he ends up looking like this. So now we've just come down a little bit, and we've passed through some saddle. And notice there are two components. There's this component, and there's this other component. But notice how you can isotope this. You can take this part, and you can pull it in. And so when you pull it in, pulling him in, you end up with just a little round disk right here. And this part, you can just pull in until you just get a round one right there. And then you can just cap those off. So you just get two components that you cap off. So here's another way to see that this original knot is actually slice. If you don't like the pushing in, you can also pass through a saddle to undo the ribbon, leaving you with just disk. So you can get rid of all the intersections by just pushing the ribbon through a saddle. We happy with this? I think you should be. So this knot's actually the knot, what's it called? It's the knot we started off with. What's his number?
6-1.
Yeah, so this is actually the knot 6-1. And so this is another way to represent 6-1. So before we had a very different representation of 6-1, right? Like before we represented 6-1 as this guy. Da-da-dun, da-da-dun, 1, 2, 1, 2, 1, 2, 3, 4. Before I drew 6-1 like this, and I'm saying actually he's this, the equivalent by isotopy, the isotopic. And so where this is how it was originally. Now here you can see it bound some ribbon. Here you can't see a ribbon like that. Because right here, if you try and make this bound a ribbon, it won't pass through each other in an arc. It's a clasp. And a clasp isn't allowed here. It has to pass through itself as it's specified here. It can't pass through it in a clasp. So we had to change it to some way that looks ribbon. But that might lead you to a question. If you start out with some knot that's slice, can you always isotope it around so it actually bounds a ribbon?
The knot diagram.
Yeah, the knot diagram. So we saw that if it's ribbon, you can push it into the four-ball and make it slice. But this guy, we knew it was slice not because it was ribbon, but because we showed that it bounds a disk. If you began with something that's slice, can you always move it to something that bounds a ribbon like this? What do you think? No. Who says yes? Anyone think yes? No? Here we could. Is anyone? Well, it turns out we don't know. So this is an open conjecture. So for all of the sliced knots we've been able to test, we've been able to show that they're ribbon, or we just don't know, but we've never been able to find a knot that's slice but not ribbon. So it's an open problem. And we haven't been able to prove that slice does imply ribbon either. Okay.
So does that mean that so far, we've always found knots that you can slice and ribbon?
Well, this other slice knot that we had over there, what was that? That was 8-8, right? So 8-8, you can look at it and be play around with it for how long and try making it a ribbon. And it's you play around with it for 10 hours, you can't make a ribbon. Does that mean it's not ribbon? I don't know. It's kind of tough, right?
But it hasn't been disproved.
That's right. We haven't proved it or disproved it. So it turns out 8-8 can be represented as a ribbon knot. But there are more complicated slice knots you can imagine would be very difficult to actually show if it's ribbon or not. So this is an open problem, so I wanted to mention that in passing. But hopefully I've convinced you that this property is reflexive now. So we have a few other properties we want to show of it. We want to show that concordance is not only reflexive, but to show its equivalence relation, what else does it need to be? Yes, symmetric. So we want to show that K is concordant to J implies that J is concordant to K. Well, let's just think about this. If K is concordant to J, that tells you that K connects some, the mirror of J is slice, right? And then what do you want to show here? You want to show that minus, so the mirror of J connects some K is slice. But the mirror of J connects some K is the same thing as K connects some the mirror of J. We talked about before that connect sum doesn't care about the order. You can always swatch the order. It's the same knot. But that's the same thing as the mirror of K connects some J, connects some the mirror of J. So we want to know if you know that K connects some K connects some the mirror of J is slice, how do we know that its mirror is slice? So given that a knot is slice, do we know its mirror is slice? And it's like, well, what does it mean to be slice? It means you bound a disk. When you take the mirror image, you obviously still bound a disk. You just take the mirror image of the disk. So if you start out with something that's slice, its mirror image is still going to be slice. So this one's not hard to show. If K is concordant to J, then J is concordant to K. And so that leaves us with one last one, and that's where we want to show this is transitive. In particular, we want to show that if K is let's say K1 is concordant to K2, and K2 is concordant to knot 3, K3, we want to show that implies that K1 is concordant to K3. And the best way for me, I think, to show this is to instead give a slightly different definition of concordance, but an equivalent definition. So here's an equivalent definition. So, and this is actually the much more natural definition. So what does it mean that K connects some minus J is slice? That means you have some picture where you have your K, you have your minus J, and it together bounds some disk in your 4-ball, right? That's some disk. And so what I'm going to imagine doing is I'm going to grab J and pull it down along your disk. This is going to look kind of weird. I'm going to have K up here, but then going along the side of my disk, I'm going to pull J to the bottom and flip J over. And so flipping it over is going to undo the mirror. So on bottom, I'm just going to have J now. And little line connects summing them. And now this disk that was bounding it is still some disk that's bounding them. But you have this little line connecting them. And then what I can do is I can just seal this up. There's a little gap here that I'm just going to seal up. So now I've just sealed it up. And now, instead of talking about K connects some minus J, it's just K and J, but they're connected by some cylinder. See that? So equivalent to this weird definition, we'll just say that K is concordant to J if there exists some cylinder, in this 4-dimensional space, which I think of as a bunch of slices of 3-dimensional space. So I'll think of it as S3 cross the unit interval, where down here I began with like S3 cross 1 and S3 cross 0, and I kind of move throughout as I tell the story. If there exists a cylinder that has boundary, that with boundary K in S3 cross 0 and J in S3 cross 1. And remember how the disk had to be nice and smooth to avoid singularities? I should probably have some word in here like there exists a smooth cylinder. Yeah, that's right. We want to avoid those singularities of things pinching. So that's what it means for two things to be concordant. There's a cylinder that co-bounds it passing through this 4th dimension. And if you think of it this way, well, now it's quite obvious that it's transitive. Because if you have some K1, and there's some cylinder that connects K1 to K2, so they're co-bounded by some cylinder. But you also know there's some cylinder that co-bounds K2 and K3. Then you just concatenate those cylinders to get a single cylinder from K1 to K3. You just glue the cylinders together. And so that's why it's transitive. So let me just end with 1 or 2 quick examples of concordance to help us wrap our minds around it. And then we'll continue next time. So yeah, let me just make 2 remarks. The first one is, what can we say about slice links? Or slice knots, I'm sorry, slice knots. Well, if you're a slice knot, that means you're some K. And as you go down, you bound some disk, right? But what you can imagine doing is taking some little point on that disk and just deleting the neighborhood of that little point. So then you remove the little neighborhood about that point, which would leave you with just a little unknot on the bottom. So to be slice means that you're concordant to the unknot. Slice knots are concordant to the unknot. Is that clear? And if you're concordant to the unknot, you can just fill in the unknot to get a disk. So it's equivalent. If you're a slice, then you concordant to the unknot. If you're concordant to the unknot, then you're slice. Bounding a disk in the 4-ball is the same thing as having a cylinder connecting you to the trivial knot, the unknot. But this raises some issues. We say that concordance is an equivalence relation, but remember we just showed that, what was it, 6-1 is slice, which means it's concordant to the unknot. But check this out. For a 6-1, if you start calculating invariants, like we talked about the Alexander polynomial. If you calculate the Alexander polynomial of 6-1, it comes out to be minus 2t plus 5 minus 2t inverse. What's the Alexander polynomial for the unknot? Do you guys remember? It's 1. They're different. Concordance does not preserve the Alexander polynomial. It's like this is not an invariant of concordance. Concordance is a new equivalence relation, but the Alexander polynomial is not preserved. So what you might say, well, how about the Jones polynomial? You know, that's a nice one. For here, it comes out to be t squared minus t plus 2 minus 2 to the minus t plus t to the minus 2 minus t to the minus 3 plus t to the minus 4. What's the Jones polynomial for the unknot? The Jones polynomial is not preserved under this new equivalence relation. It's not an invariant of concordance. It's an invariant of isotopy, but not of concordance. How about Yeah, the genus, or the determinant. What's the determinant of this guy? He comes out to be 9. What's the determinant of the unknot? Could we call it 0, 1? I guess 0 makes sense.
Like, I guess it would have to be 1 because you think of like next song.
Well, it's certainly not 9. It's not preserved. It's not preserved. And in particular, colorability is not even preserved, right? So like nothing is preserved. None of our invariants seem to be preserved. So you might wonder, are there new invariants? Are there invariants that are preserved under concordance? And it's like, we're going to talk about that next time. And we're going to define at least one invariant of concordance. A lot more I want to say, but let me save it for next time, and we'll stop there.